Welcome everyone. Today is February 28th, 2017, and this is the CNPS Saturday Morning Science Chat. And I'd like to welcome everybody here. And just for general announcements, I have our slide here. So I encourage you to visit our website, naturalphilosophy.org, join up and or renew your memberships. And we are working on trying to get people to move their discussions onto the new forums, which is forums.naturalphilosophy.org. So give it a try next time you want to post something. And we also have Facebook. Okay, so I think today we're going to talk a little bit about what photons and what light is and how that all works. So what I want to hear about first is what other people think about what light is. So who here thinks they have a theory about like what a photon is, or whether that's even a correct terminology to be using? Have any volunteers?
Well, I have a theory about photons, if you want.
So do they exist?
Don't give us the whole theory. Just give us a thumbnail sketch.
Yeah, give us what do you think a photon is in 30 seconds or less?
A photon is a string of solutions of the second order partial differential equation, and the members of the string are warps. It are one-dimensional shock fronts that are spitted out at equal distances. In fact, also on equidistant instants. And therefore, it looks quite similar to a wave, but it is not a wave. It is a series of one-dimensional fronts. Otherwise, it cannot reach these huge distances from billions of years coming here and are still ready to be detected, have sufficient energy, amplitude left to be detected. A wave cannot do that.
Why would you say a wave cannot do that? Why wouldn't
a wave without a waveguide, a wave goes in all directions. So it loses very quickly its amplitude.
Okay, well, that would be a conventional. So that is one argument about a wave. Well, all ordinary waves that we see, like sound waves, do dissipate fairly quickly.
Yeah, they fade away fairly quickly. There are also three-dimensional, so spherical fronts, shock fronts, and I call them clamps. They exist as well, and they also fade away fairly quickly. And in fact, elementary particles are constructed from these clamps.
Well, aren't shock fronts also waves? So what's the difference?
Shock fronts are not waves. They don't have a frequency. They are one-shot phenomena. They are generated by a single trigger, and a wave must have a periodic harmonic trigger. Otherwise, you cannot raise a wave.
Well, that's not true. In a wave tank, I can just like go bloop, and I can create one wave, and it goes across the wave tank.
That's more or less what you then get is what I call a plop, or it depends on the number of dimensions that are available. If you have one-dimensional available, then you get this one-dimensional shock front. If you have two dimensions available, then you get a kind of plop. It's not a shock front. And in three dimensions, again, you get a shock front, because
I get rather confused when somebody says one dimension.
And one-dimensional or in three-dimensional. Also in three-dimensional continuum, you can trace one-dimensional shock fronts, and they keep one-dimensional.
Well, I don't see the distinction still between a shock front and a wave. To me, A shock front is just a wave with a single cycle, but it's still fundamentally a wave. It's still a compression wave.
No. It's a peak, and it stays. It's keeping the same shape when it moves away. It doesn't look like a wave in any sense. It is a peak, and it keeps its shape, and it moves away. And the three-dimensional one is also keeping its shape, but its amplitude gets smaller when it makes some distance.
Hans,
Sorry, yeah.
am I the only one that's confused by a single dimension, by a one dimension? Because when you say shape, how do you have shape in a single dimension? I'm confused about that. You know, are we talking
If you draw a curve,
property dimension?
if you draw a curve and you make how you call it a jerk up and down, then you get a peak, and this peak goes running away from you from the trigger point. That's what's happening in a field.
But I can't draw a curve in a single. I
No.
can't draw a curve in a single dimension. Am I the only one that's confused about?
But if you look at the solutions of the second order, for example, the wave equation is such a second order partial differential equation. If you look to the solutions, you see there that equation has several solutions. One of them is waves. Another type is
for yours.
Sorry. Someone was in between. It has several solutions, several type of solutions, and in even numbers of dimensions, you don't get shock fronts, but in even numbers of dimensions, you get shock fronts as solutions of this equation. So they're all solutions of the wave equation of this second order differential equation. I'm sorry, I'm Dutch.
Well, I didn't
Okay,
understand any of
so
that
I think
because
we have I think the real first issue is that we have a problem with definition of what a wave is, and that seems to be a problem there.
Tax registration form.
No, that's done nationally. That,
Well, I agree with Franklin that which is just a single pulse, or you like a
It's a pulse, but
canal
not a wave.
maintains its shape and
It's a moving pulse.
I agree with
A moving
Franklin.
wave package.
Waves don't need to have period.
A wave package.
Well, a wave can, whether multiple pulses is still a wave. So I think it's just a definition that we're distinguishing here. I think we're talking the same thing.
If a wave package is starting to move, then the wave package is going to disperse. After a while, it is no longer a single plop or so. It disperses into several components, and they go with their own speed.
Well, I still have a problem with the idea that you don't think a wave can propagate for long distances, because I actually don't have any problem with that. It just decreases by 1 over r squared, which is a very fast decrease. But that is the rate of decrease that we know for photons or light. So I don't see there's really a problem with that.
You must see a shock front as a kind of tsunami-like thing. It keeps its shape. It keeps traveling, but it keeps its shape. Only
tsunami is a wave.
Spherical ones, the amplitude goes down. And for one-dimensional ones, the amplitude keeps the same.
Well, for amplitude, the amplitude must go down. I mean, if you have something where the amplitude does not go down, you would be talking about something which is not light or photon-like.
No, it doesn't. It doesn't go down. As not for the one-dimensional one. That amplitude stays a constant.
Well, there is no one-dimensional thing. If I have a candle and I'm measuring the light intensity, it drops off over 1 over r squared. So definitely
that's a
something is
spherical
dropping
one.
off.
That's a spherical one. But that doesn't happen in the one-dimensional one. It does
Well,
happen in
there
the three-dimensional one.
there really is no one-dimensional one, I don't think. So that would have to be something in your
There is
mind.
one. Look into the solutions of the wave equation. There you find one.
Well, I mean, you can't look into equations. Equations aren't physics.
Yeah, but these equations, for example, are treated in Wikipedia. If you take on Wikipedia and look to the solutions of the
A one
wave
dimension would
equation,
just
then they show what kind of solutions there are. And
But
there are
one
different
dimension would just have one variable. A single variable can be
I think you need to look at what
a
light
single
can
variable can
do.
be the only thing that can be defined in one dimension.
Concerning
Well,
concerning one-dimensional things,
this
I mean,
this
light
happens.
has properties that are which are unique. Now, you have light that comes off, say, a candle, and that clearly goes off in a
That goes off
spherical.
in all directions.
Yeah, that goes off in all directions, all
There you
frequencies,
have the code.
spherical. But you have also things like laser light, which
Yeah.
really do not go off in all directions. It's like I can take my laser beam and I can measure the light
Well,
intensity.
it's
No. The fact that doesn't go off in all directions is the question that it's interference that keeps this going into nearly one ray. But at long distances, it still goes off in many directions. It doesn't
Not
keep.
really. No, I mean, we have a laser guy can shine a laser
I
beam
explained this to you
Several
several
miles.
months ago, Franklin. This is completely erroneous concept on your part. I disabused this several months ago, and you didn't pay any attention. I explained it to you. If you want me to pull out the books, I'll show it to you. You're completely wrong about this.
No, I'm just pointing out a particular property of light, and that
You're
it has
completely
this.
wrong about this. Completely, totally wrong.
No, I believe no. If I have my simple laser pointer and I point it like 1 foot away from the wall,
Yeah, that's
it
only
creates
because
a
of
very
the
bright
fact
point.
that I explained this to you before. Okay, it's like a microwave antenna, microwave dish antenna. The bigger the aperture, the sharper the beam. And in the case of a laser pointer, the size of the aperture is very, very large compared to the wavelength of light. And so it creates a very, very sharp beam.
Yes, but
But
that's something that sound cannot do. We cannot create such a concentrated
Well, the wavelength of sound
beam.
is too big to be focused in using an aperture type of reflecting device. This is well, in all the books on lasers and everything, this is well explained. Okay, but that's just throwing another issue out there to create confusion in my mind.
We go back to discussing photon or not?
Okay, let's start with photons. So the idea of a photon is that it's like a particle. So is light like a particle, or is it like a wave? Who would like to handle
Okay,
that
so
one?
that's really what the issue is. Okay, and that's the root of the issue, and that goes back to historical hundreds of years that what is light, and usually the books trace that back to Newton's theory of fits, and he thought that light was a particle, and then other people disagreed and said that it was a wave. So that's kind of where that story starts with Newton. The modern theory goes back to the discovery of the photoelectric effect, which Bill Lucas is kind of an expert on. But my understanding is that was discovered by Hertz. Is that not? And when he had ultraviolet radiation, he discovered that the sparks in his radio detecting apparatus were responded more sensitively when there was ultraviolet light present than not. And then so you move forward that. Einstein basically proposed this idea of a photon, which was a particle of light, which kind of was a return to Newton to a certain extent. And that's where and of course, Planck had come in with this idea of the black body radiation could be explained by assuming that light was quantized. Now, it's not really clear to me that that's the same concept that Einstein had. That's sort of something for somebody who's a history of that to discuss, I suppose.
Planck was talking about black body radiation, and Einstein was talking about how an electron can be freed by a photon, and vice versa, that an electron can free a photon.
All right, I have an idea which I would like to throw out and get some feedback on. That is, a photon is created from an atom when the electron is in an excited state of the atom and it goes to a lower energy state of the atom. It creates and emits what's called a photon, and the photon would be a soliton, a localized non-dispersive something, and it can create that because it's in a distorted environment as caused by the positive charge electric field and the magnetic field of the nucleus. However, if you take an antenna and you have conducting electrons in a piece of metal and you oscillate that, that is not creating photons. That's creating electromagnetic waves that go in either spherical direction or certain antenna shapes. It could be dipole kind of distribution. But the photon is created only when you have this nonlinear environment of an atom where the positively charged nucleus and the negatively charged electron creating that environment very uniquely to that kind of setup. And so when an electron is excited, it absorbs energy from the electromagnetic wave. But when it's decreases to a lower energy state, that environment is not linear and creates a photon as a soliton. They're very different. I think a lot of people, or at least in my mind, it's very different, would, from conventional teaching, say an antenna of any kind, yes, it's oscillating, putting out the waves, electromagnetic waves, but that's made up of all these photons. I don't see that. I see it because the antennas are just going in all directions. Even if you have focusing antennas, they're still not precise like a ray direction. Whereas when the electron goes from an excited state to a lower state and emits energy, that energy is very directional in one direction. And that's why I think it's a soliton non-dispersive wave, because you can get then that very precise direction of the emitted photon.
Okay, so let's, can we summarize? I'm not sure who this is talking because there doesn't seem to be a name associated with. So who is it that's talking?
This is Bob Gray.
Okay, Bob. So this is kind of a, I think kind of an important issue that you're talking about. So what is your position? Could you summarize your position a little simply for us? What are you saying?
I'm suggesting, throwing it out for discussion, that there is a photon
Can't hear you.
very uniquely, and electron excited goes to a lower energy state, whereas in other things where you have electromagnetic waves, those waves are not composed of photons. They're composed of electromagnetic waves. And the reason is the environment in which these are generated are different.
Yeah, there are several processes that produce photons, not only atoms. When you have pair annihilation, then you also produce photons. And for example, Bremsstrahlung also produces photons. So there are
Well, I
more
think now
sources.
the issue is that we're not really sure what a photon is, and the terminology photon and wave has been used. Electromagnetic wave is distinct from a photon as a soliton. Was the terminology that Bob was using. So that kind of, the puzzle is what do those words mean? Um, and I guess that's kind of what I'm kind of wondering. I'm not exactly sure whether the distinction is meaningful or not.
Well, let's try and solve the puzzle.
There is an
that's
important distinction. The waves can happen in all kind of continuums, and also these shock fronts can. They are just.
Can't hear you.
yeah, what happened to your hair, Hans?
Something froze.
Well, I think it is important because now, usually when we're talking about photons, we're talking about, let's say, visible light, I think. And this is like the difference between photons, visible light, and say radio waves, which is what I think he's talking about, that there does seem to be this distinction between radio waves and photon light waves seem
Well,
to be
he was,
distinct.
well, a couple of issues here. One is bringing in the radio antenna, sort of, that's kind of the issue that I was talking about with you earlier about the focusing of the energy in a laser beam, and so in effect, a laser is sort of like an antenna, okay, and so now you're getting into this whole issue of what is the physics involved, and he's talking about an atom. And when I was in school, they had these. I remember that they derived these equations on how an atom, when it changed from, the electron changed its state from one atomic level to another, it radiated kind of like an antenna. And I thought that was really kind of cool. So the issue is, do atoms radiate like antennas? But I think that's getting a little ahead of the discussion. I think the real discussion really boils down to the idea of a photon as a particle or a photon as a wave, and that leads you to the wave particle duality that they talk about in quantum mechanics. So the question I think you have to ask first is what is meant by wave and what is meant by particle, and I think you need to sort of get those two concepts separated before you can go further.
Right. I agree with that. There is an aspect of what you said I didn't agree. The laser part, that's all from atomic excitation and de-excitation. So I would not put that in the same category as an antenna. I do agree with you, a laser light over a long distance does have a spread to it. The difference I see is in the concept that I have of an antenna is you have electrons which are accelerating and accelerating, deaccelerating, causing waves, but not photons. The difference being a photon, the way I'm thinking of it, is a soliton created in a nonlinear environment and has a very precise direction. Now, a soliton is composed of lots of waves, to make a wave packet. So that's the way I'm thinking the difference between a photon and an electromagnetic wave. In the atom, when the electron goes from the higher energy state to a lower energy state, that is cause the generation of a photon in one direction. So I don't see the de-excitation in an atom as acting like an antenna. Or take a charged particle and accelerate that or de-accelerate that, in my mind, is not generating photons, but it is generating electromagnetic waves.
How then do you explain the quantization of photons? They have different energies.
I'm sorry, the what of photons?
The photons can have quantized energy. They come in definite quanta of energy.
Right.
So a soliton has only one kind of energy.
But when you go for like a hydrogen atom, it has many energy states, eigenstates. And if the electron goes from one energy eigenstate to another, a lower, it is generating a soliton for that amount of energy and in a very specific direction. And that is what's emitted.
So the soliton has different shapes.
For different energies.
Yeah, a different shape for a different energy. That's what you're saying.
Yes.
Well, I think maybe we can combine these ideas. So, for example, Hans is talking about a shock front. And so perhaps what happens with this atomic case is that when the electron transitions, it creates that one shock front. But it's still fundamentally a wave, right? But it's a shock front wave which is very directional. Perhaps we can meld these together.
Why don't you try defining what a wave is before we get any further?
I was telling that a photon is a string of these solitons or these shock fronts. So
now I'm a little bit confused,
the number,
because I would have thought that the
number
photon would be one of the individual parts, but you're saying a photon is a string of the parts?
Is a string of these what the other guy called a soliton. A photon is a string of such solitons that are emitted at equidistant instants.
Why a string?
Then at equidistances, a photon has a fixed energy, and these warps, I call them warps, he calls them solitons. A warp has a single bit of energy, and if you send out 100 of them, you send out 100 parts of this of that energy, and in that way a photon can have a quantized energy. And in that way you get several colors of photons out of an atom, and these are monochromatic colors.
I think I understand what you're saying, Hans, and it's very interesting. But I suspect because of the terminology that it's kind of confusing the other people. And I might not exactly be clear on my understanding either, but the terminology is a bit difficult to follow. And we seem
try
to
not to get wrapped up in the terminology.
Huh?
Try not to get wrapped up in terminology. So I'm trying to.
Terminology is the key to the whole thing, because we're using words to transmit concepts between human beings. And so that's really what it all boils down to. What are the words?
We're trying to put it together in a way that everyone can understand. So that's why I'm trying to build a composite model of what people are talking about. So like this would explain the quantization of light, and it would explain why light is, say, different than the radio waves. So Bob is saying that light only comes from atoms. Maybe we can establish that what we call photon only comes from these atomic processes.
No.
Versus radio processes.
there are several sources of photons. One very important one is when pairs of electrons, an electron positron pair, when that annihilates, then two photons are generated.
Yes, but
So that's also another source of photons.
yes, but notice what you're doing in that. The environment again is such that you have a positive charge and a negative charge, and they're going to, as you say, they're going to annihilate. That environment is so different than a charge-free free space that you might talk about in Maxwell's classical electrodynamics, for example. The environment becomes more nonlinear in this positron electron kind of environment, which allows for the generation of nonlinear waves, that is the soliton, which is the photon. So yes, I'm talking about an atom and its energy states generating these solitons or photons, but there are others, as you say, like the electron and positron, which has enough electromagnetic charge or interaction with the medium, if you will, the quantum vacuum, whatever it is, to allow for the generation of nonlinear waves, these solitons.
What's nonlinear about a soliton?
Solitons are non-dispersive waves. They are, if you want to express it mathematically, it's a nonlinear differential equations, and that's where I'm using the terminology nonlinear from.
It's a solution. It's a perfect solution, a linear solution of a linear second order partial differential equation. There's nothing nonlinear to this.
Well, I think it's more important that the wave is quantized and goes off in a particular direction.
Yeah.
In the case of positron-electron annihilation, I would actually consider that an atomic process, because that is, once again, an electron falling down into a potential, which is the same as basically a hydrogen atom, right? It's just like, so I would consider that to be one of the same things.
I also dispute that this is an electromagnetic wave, because the electromagnetic field is the carrier in radio waves, but a photon can have another carrier.
I need to cut in here.
And it has, in fact.
Like, excuse me, I need to cut in here just a little bit. I was not able to answer the soliton question right from memory, so I just looked at it on Wikipedia. Wikipedia says solitons are caused by cancellation of nonlinear and dispersive effects in the medium. That is what I mean by the soliton being nonlinear, non-dispersive, holds its shape as it's being translated.
It's basically the media that's nonlinear, the characteristics of the media.
Yes, I'm sorry if I'm using a confusing description. I'm a little nervous talking here, actually, and things don't come out the way that I'm thinking.
No, that's understandable. Yeah, that's the way I view it also, as the media has a nonlinear characteristic to it, but
Yes,
the soliton travels through that media. And I believe that's not much different than the, Hans's media carrying the wave.
My warp is not a soliton. The warp is a one-dimensional shock front, and it is a solution of the wave equation. And the wave equation is a linear equation. It's a linear differential equation.
But we still went into an issue of, okay, single dimension.
Someone's causing a lot of noise here.
Yeah. So that's why I'm saying with the electron and positron, it's creating a nonlinear medium then. Thank you very much. Or in an atom, it's has the positive nucleus and the electron, again creating a nonlinear medium for the generation of these solitons. Whereas in antennae or other devices, I don't see that kind of generation of a nonlinear medium. So it's generating just normal dispersive waves, electromagnetic waves, not the solitons.
Yeah, but you can create. You can also with an antenna, you can create something that comes close to a soliton. If you have nearly all frequencies at the same time and in the proper phase, then you can create a soliton.
Well, you can have a very high frequency, like, and you have focused beams of waves, but they still dispersive. And the difference is there's the big difference I see in waves that are dispersive and non-dispersive is the media that you're in. And if you have a nonlinear elastic media and you have a transverse wave, a nonlinear elastic media will support a transverse wave through it that is non-dispersive. And that's the characteristic that I give the media to carry a photon. And if you have a compressional or not a longitudinal wave traveling through that media, the longitudinal wave is dispersive. And so that's in my view the distinguishing characteristic between what an electron or a photon is and the dispersive wave, which would be more of a mass or gravitational wave, which does change at the inverse square rate, where the photon being transverse wave in a elastic nonlinear media will and that's where I think we differ, is that in an elastic media, waves do not disperse if they're a transverse variety.
So I want to see, now everyone so far has been talking about photons as being like waves. So can we all agree that whatever a photon is, that it's a wave phenomenon, and that we're not really talking about a particle?
No.
Now, I don't want people to get wrapped around definitions. Now I know you want to call your thing a warp, but is not your warp not exactly a wave?
That's not a problem. You look at the solutions of the wave equation, and that wave equation has several types of solutions. If you look at those solutions depend on the trigger that causes these solutions, and they depend on the dimensions that that take part in the process. And the wave equation has many of different types of solutions, and waves are just one of the types. There are about 4 or 5 types.
Yeah, we're just looking at solutions that actually fit into an actual media that we can define.
Yeah, but the wave equation holds for all fields. All fields can have solutions of this wave equation.
Well, what I want to find out is whether we can come to some agreement about whether light is a particle like matter, or whether it is due to some kind of wave action, which is something that happens in a medium.
Can
we come to agreement on at least that?
If a photon has a fixed length, then it can be considered as a particle. And because it travels with light speed, it also then has a fixed duration. So a photon.
Well, do you think that a light wave is the same thing as, say, an electron? See, now we know electron for sure is a particle, right?
Yeah.
So I'm saying
wait
that.
A second. You say for sure is a particle, but that's the other half of it, and it's something that Harry brought up. We have to define what is a particle too. We can't just say is an electron or is a photon a wave or a particle. We have to define what we're going to call a particle, because in my view, a particle is a packet of waves. So that so we need to define what's a particle then.
Okay, a particle is what we can see intangibly in experiments. How about that? Can we agree on that?
It's not a very good definition.
No, because we see things with light, and light, if light is a wave, then what we're seeing is the reflection or the interaction of potentially waves with other waves. So that doesn't define that, like
Let's
Harry says, it's not very definitive yet.
let's go back to what Hans is saying. I think is real important, and I agree with what Hans is saying. I'd say Hans is saying that a wave is a solution of a second order differential equation. Okay. So, in my opinion, that's the definition of a wave. So, anything that is a solution of that equation, I would say is a wave. Now, you might want to disagree with that, but to me, that's at least a definition to start with.
I think
Well, the
that's too
definition that totally
mathematical.
puts me out of, yeah, the definition puts me totally out of the picture because I don't understand the mathematical explanation of the second order partial differential
Hey, we
equation.
can't hear you. It's too noisy. Something wrong with your microphone.
Hello?
Can you
My
try again?
microphone is off. Something else is wrong. Okay, now I hear the sound's gone.
Yeah.
All
Okay.
right.
Okay.
I understand
Something
that.
else is off.
I understand that objection. That's kind of a difficult issue there. I agree with that. That defining what a wave is mathematically kind of limits, the ability to communicate the concept of wave. So that is a conundrum. So, but a physicist would probably be happy. I think Hans is perfectly happy with his definition that it's a solution of a partial differential
Well, but
equation.
Hans is a mathematician too.
I'm a physicist. I'm a
Yeah.
very bad mathematician.
Yeah. Well, I am an observer, and I can see waves, and I can see tension, and I can understand how tension can create waves, and how moving tension is a wave pattern, and that, and so
We're creating a big problem because the word wave is so overloaded. Wave is not the proper term because everybody considers nearly everything as a wave, and that's not proper.
you're right,
Wave,
and the
waves
thing is that you consider a wave to
are
be
sine waves and cosine waves. That are waves.
No, that's a cosine wave and a sine wave. That's a tsunami is a wave, and that doesn't take the shape of a cosine or a sine wave. So
Yeah, if you
again,
take superpositions of cosine and sine waves, you can make and that's what the Fourier transform does. You can create any shape with sines and cosines.
but not a single pulse.
But you can't create
You can even make a single pulse.
You can't make transverse and longitudinal waves. You can only make transverse.
The problem is a wave is a very overloaded word and um,
So
these
you'd
shock
like us to
fronts,
use
these
you'd
shock
like us to
fronts
use a
are
shock front?
these shock fronts are quite different beasts than waves are because they are well, the soliton was a good word because it means solitary. It's a single shot phenomena.
And yet
And
you
a
see the
wave
word
is always something periodic.
yet you see the term soliton wave.
Nay, it's not a wave. A wave is always something periodic. And,
But
a single shot phenomenon can be a shock front. These are two different things.
okay,
Oh, I think you're wrapping yourself around definitions.
right. I think we'll
No,
not
no,
go
no,
there.
no.
I mean, you
There's
can
a
try and make that distinction, but
I will say I'll just use the term single wave, and we'll be okay. If I say single
Well,
wave, will we be okay?
a single wave could be a
It is
sine
the
wave.
trigger. It is the trigger on the one hand, what makes the difference, and the dimension in which the phenomenon
Okay,
operates.
so now it's a
Is
single
the other
wave pulse.
distinction. Sorry,
A single wave pulse. Is that
it's
good
a
enough?
single pulse. It's a single
Okay.
pulse, a
All
single
right.
trigger, and the pulse is moving away as a pulse.
Okay.
yeah, once again, let's not wrap ourselves around definitions.
Well, we're trying to come across a reason. I guess I have no choice but to use the terminology that Hans uses. Otherwise, we were not going to get anywhere. So we'll call it a pulse, or what was
Right.
it? A shock front. A shock front.
I'm
Okay.
cool because I think people know what shock
Okay,
fronts are. It's like a single.
radio waves are multiple shock fronts coming at successive periods of time, which are equivalent in duration.
I would agree with that. Sure.
We have a radio wave. So, okay, we'll use the term shock front to avoid going on forever about what a wave is.
But that's
Well,
not a particle, right?
I'd like to bring up my little.
A shock front is a packet, a wave packet. We can consider any wave packet that has a beginning and an end as a particle.
No, I think
Or
that
a
is really.
solvent.
I would say that is the key thing. That I don't think we should be calling wave packets particles.
Okay, well,
Yeah, the problem with particle is that the particle is generated by a swarm of triggers.
the swarm of triggers are generated by
point-like,
convergence of
the triggers
waves.
are point-like, and the particle, elementary particles, are in fact represented by a hopping path, and the hopping path creates a coherent swarm of hop locations, and that's the particle. And each hop location creates also a spherical shock front.
Yes, but I have exactly 180 degrees the opposite view of what you have. The shock fronts come together and hop and converge in different locations nearby each other and create hops. So that's we're getting way off subject there.
Yeah, I'd like to throw in a point. Isn't it true that you can Fourier transform a pulse into a superposition of waves of different wavelengths?
Yes.
Well, I would like to bring up a distinction with a particle in that when you collide particles together, they reflect off of each other like billiard balls. And my objection has, I mean, because you're trying to always say that a particle is made out of waves, which I have I'm extremely violently opposed to that idea. And
yeah, you're gonna have to get over that one probably.
No, that's the only way I can express it, because intuitively, I believe that particles do inherently exist as objects in space, which take up finite space. They do exhibit the property that they take up measurable finite space, and they have a ponderable surface, and that they are not made out of waves. So like
you're
an
have
electron.
A real problem with wave particle duality. You basically decided.
Yes, I have a huge problem.
Duality. There's particles but no waves.
Yeah.
There's no duality.
Exactly. That's why. That's why I have such a huge objection to this idea that particles are made out of waves. Now that's just expressing my personal opinion, but I express that because waves pass straight through each other, so they cannot possibly display this elastic property that particles have, that they bounce off of each other.
And yet you use waves in your documentation.
Can I make a point?
Okay.
Yeah, I like the idea that particles are made from interference pattern of waves. So maybe an atom is a wave field in 3 dimensions spinning, but you're leaving out density. When you go from a low density of an ethereal type of structure to the high density of the nucleus of an atom, you become the solid thing that it is. So you can't have something of high density impacted by something of low density. They can be made from the same thing, except at a higher density, it acquires a certain property that we see as a particle, which that something of a low density doesn't have at all, that can be passed through. Okay.
Well, but you mentioned density, and then you have to get into density of what, because now
the density of the geometry of the nature of the thing. It's more complex and more involved and more structure. It's like taking something with little structure and let's say water, okay, and then putting at the center an iceberg, okay.
Right. Okay, but But basically, when you're talking density, are you talking density of a particulate ether?
Yes, but I
Okay,
think that
see,
same
and
ether
that there we
becomes higher
distinguish too.
density into the atom. So the atom
I,
creates the ether, a field around it. The sun would create an ether field, let's say, to the heliosphere. You got maybe millions of miles away. And
yeah.
I think that the entire ether is basically a fluid. You could think of this as a three-dimensional fluid made of
Okay.
photons. You don't see them. They're there. Oh, they only are seen when they vibrate. And
I
they're
think
maybe a
we got to
structure.
get back to particles because we're going to get into what ether is, and there's a distinction between. I agree with you on energy density or on density, but in my view, it's the density of energy and not the density of particles.
Energy
Because
is
particles
is
have
a
yet to be
misunderstood phenomena.
correct. I
Energy.
agree with that one too.
Okay,
I
so
think we need to
that
get
whole
back
thing.
to photons. To
Well,
get
I think
back to
we were
photons,
just we were discussing particles last, Franklin. What is a particle?
yes. So
And that was
only
what we
in,
were
in
discussing.
only in terms of whether a photon is a particle.
Well,
Photon
let's go
is
back to the net.
two-dimensional a construct in terms of its property. When it vibrates, it acquires mass. As a two-dimensional property, it is not having mass, and it's not. It's what you'd say not a particle, but it is a particle in the sense that because it's an interference pattern of waves, it's always a particle, even though it doesn't have mass. It has a structure because it's relating to its field as an interference. That's what all the particles do. But when it vibrates, the velocity that's added adds an additional property which carries it and acquires mass. So that whole Higgs thing where you get a collision and you get two photons, well, each one of those is two-dimensional, but you combine them, you're at a level of force, and force has mass and acceleration, but it's broken down. They break into two photons. You're at two-dimensional, two photons. Okay, they have no mass. So what gives mass to anything is not the particle; it's the property, and that property is something two-dimensional, which is a photon going into something three-dimensional when it moves.
Okay.
So mass
Now,
is not something that is embedded in a particular particle. It's a
Now we have
quality
to
of property.
now we have to go back and define dimensions because we're
Okay, I
talking
just
about
wanted
one,
to
two, and
say that.
three-dimensional objects.
I
All
think we're
objects are
getting
three-dimensional.
Okay,
Even
back
two-dimensional
to Franklin.
properties are three-dimensional. The only thing
Let's go
that
back to
distinguishes
Einstein, please.
three-dimensional from two-dimensional is that the properties are two or three-dimensional.
Can we go
Everything
back
in
to
the universe
Einstein,
has
please?
volume. There's no such thing as two-dimensional anything. It's a question of geometric construct that differentiates two-dimensional from three-dimensional. I can call the ether two-dimensional in its sense of property, but it has volume. It's
Okay,
three-dimensional.
so wait a second. What you have to distinguish the difference between is a geometric dimension and a property dimension because that's what you're
correct,
getting
but
into.
everything is it's multi-dimensional. There's no
How-
one.
how do we-
Everything is multi. Let's try to see if we can clear this up because we have
That is another big
multi-dimensional and we have
scientific
multi-property, and we use the
misnomer.
term dimension too freely. Also, like Hans says, we use the wave creation too freely, but a dimension is also used quite freely as referring to three-dimensional geometry, as opposed to a dimension being a property such as temperature, density. Those are dimensions or properties of a unit.
Correct.
So that
No, I agree
adds
with
to the confusion is the overuse of the term dimension.
Yes, but in the real world, in the world of physics, there is no two-dimensional. It's
Okay,
all
well, let's not
geometric
dwell on that.
volumetric.
Let's not dwell on that point.
Okay.
So,
Well, I think it makes it a lot easier to understand each other if we understand when we're talking about a proper dimension and a geometric dimension. We have to prefix the word dimension with geometric or property.
That's right. Correct. I agree with that totally. Okay, I didn't mean to interrupt your thing. I just want to throw those in there.
All right,
Okay,
let's
I mean, a
let's
lot
try
of
and
this stuff,
stay on topic here.
you can't talk about
I want to go
particle
back to
and
I want to go back
photon
to the
without talking
whole.
about density.
I want to go back to the whole thing that Einstein proposed, where he proposed that light is a particle. That's really what we're talking about. That's really where the nexus of what we're trying to get at. First off, we don't really know what Einstein meant by particle. You seem to know, okay, but a lot of other people don't seem to know what Einstein meant by particle. What did he mean by particle?
Well, this was all based off of the photoelectric effect. Now, my interpretation is that he said it was a particle because the quantization that was happening with the photoelectric effect, that it didn't matter what the light intensity was. The only thing that mattered was actually the frequency of the light. So he concluded that light must come in quanta. And so he equated the quanta with being a particle, because obviously a particle like a piece of sand is quantized. You can see it; it's one little thing. So that's the way I see that he's thought that light was a quote unquote photon, as being quantized as containing only a certain amount of energy. And I think we've all been saying that, like Hans is saying, shock front or solitons, that there's a quantized amount of energy that comes out of these atomic processes. So I think we may be able to find some commonality in that.
Yeah, but they come out in strings.
Personally, I find it extremely violent to logic to call a quantized packet of light a particle. And I think that's where the confusion is. I really don't want to call a quantized a photon a particle.
I prefer to call it particles. I prefer to call it particle.
If you take a shock front and say that shock front has a single bit of energy, and you have higher energy photons, then you need more of these shock fronts in a string. So if this string has a number of members, then that energy is that number higher. So this string must contain so many shock fronts.
Well, maybe let me try and explain something. So I'm kind of listening to what you guys are saying. So let me see if I can so we're just going to like build a new theory based off of what we've been talking about so far. And maybe we can come up with something that we might be able to kind of agree with. So based on what you're saying, let's start with where photons come from. And let's just agree that photons are the things that are generated by these atomic processes. So like I said, there might be some exceptions, but I think from what I'm hearing, the distinction that people want to be making is that photons come from these atomic processes. Otherwise, regular EM waves come from antennas, from electrons being put and removed from antennas. But it seems that we seem to be moving towards the idea that photons are unique because they come from these atomic processes, and that so we have a different kind of what Hans is calling a shock front, but it essentially is just a single pulse wave. Those single pulse waves coming from the event of the electrons falling from a higher energy to a lower energy, creating this shock front. But it's like a single pulse. It's very directional. So this pulse goes out. It's very limited. It goes out in a particular direction, and that's what we generally consider a photon, but only because it has a very quantized energy.
It doesn't solve your problem, because you need to have a series of those shock fronts in order to.
Well, yes, you do. I mean, when an atom is excited, it will continuously make these shock fronts. Maybe not necessarily equally spaced, but they will create these shock fronts, and depending on how much how far the energy, how far the electron falls in the potential, it will create different amounts of energy in each shock front. That's why we get, say, the different frequencies in like hydrogen. Like in hydrogen, we see very specific frequencies. Yeah. And depending on whether it's going from like level 3 to level 2 or from level 3 to level 1, it creates greater or lesser amounts of energy, and that's reflected in the actual frequency of these shock fronts. Now, it is interesting to note that even when you're talking shock fronts, that these photons still have a specific detectable frequency. Like we'll see the red ones, we'll see the blue ones, we'll see the green ones.
A single emission event creates a string of these shock fronts. And the number of shock fronts in that string determines the color.
Do you have a mechanism for creating the string? I can see a single shock front mechanism, but I can't see a mechanism for the string of shock
yeah,
fronts.
I don't see that mechanism either. I mean, I think that you don't necessarily have to string them together. I think in atomic processes, we can see those coming off like kind of randomly, but they would be coming off with a specific pulse width. And it's that pulse width which determines the actual frequency.
I see a photon as being having a wavelength, which I like describing light as having a wavelength, but I don't like having to describe light as a frequency, because to me a frequency is, like you say, a repetition of cycles or wavelengths, and that's where I make a distinction. I think a single shock front with a single wavelength can distinguish between colors of light. Where 90% of that energy of that wavelength exists determines 90% of that energy of that photon exists determines the fundamental wavelength of that photon. I'm not sure if I can see the mechanism for the repetitive shock fronts. That's what I'm wondering, is how, Hans, you get the mechanism that creates multiple shock fronts out of a single.
The energy is not in the shape of the front. The energy is in the number of fronts that are emitted. There is one event, and then a number of these fronts are emitted. And the emission duration is a constant. Also, the length of the string is a constant. But the number of fronts in the string, that makes out what the energy and what the frequency is.
Okay, how do we measure those number of fronts that you're talking about? Is anybody, am I getting sidetracked from a conversation here?
I wouldn't know how to measure it.
We have to come up. I mean, it's a good question.
The atom is capable the atom is capable of counting the number of fronts that are coming in, or the number of fronts that are going out. That is
okay.
The atom is the measurement.
So I'm looking for the mechanism. I'm looking for the mechanism to do that, and that's what I'm missing. Is I don't see. I can see the mechanism where when a charge changes orbitals or changes the shell of an atom, that being a single event that it changes in a single from this shell to that shell. But I don't see how that changing from one shell to the other is more than a single event that can create a single shock front. I don't see the mechanism.
That's not what he's talking about. Cornelius, are you familiar with what a plane wave is in EM theory?
I know what a plane wave is, but I don't consider it an EM at all. I consider it gravity.
Well, then
mass wave.
In EM theory, they talk about a plane wave. You familiar with this concept?
Which is, yeah, a longitudinal wave, yes.
Well, no, it's a flat thing. It's a two-dimensional thing, and then they say that you have an E vector and an H vector. It's a two-dimensional.
Are we talking two-dimensional geometric or two-dimensional?
Okay, you don't know what I'm talking about, so forget it. All right.
Well, let's go back to Corey's question, which is how does it create these shock fronts? So Hans has given us one idea. I personally don't.
This is my point. My point. You're just putting together words and shock fronts. That's not, you know, I mean, come
Well,
on.
we're trying to put together a solution here, right? So we're trying to answer Corey's questions, like how is it, because we can see how a shock front could happen, but what we don't see is how multiple of these shock fronts could happen and how they could link themselves up into, like, you know, a continuous set of pulses. I think that intuitively, just looking at it, you'd think that if these little shock fronts get created by the individual transitions, that I don't see that they need to line up.
Okay, Franklin, please stop. Please stop talking. You have to explain how energy goes out of the atom or out of the antenna. Okay, the shock fronts that Hans are talking about is the energy that's being carried by the wave, but the wave is visualized as a very small slice. You understand what I'm talking about?
Excuse
To
me,
get
Harry.
a photon, you have to add up a whole string of these slices. To get the total
Why?
energy in the photon, you have to add up all the parts.
No, I don't think so. I mean, we're like I
Well,
said,
then
we're
you
why
should
are
be
they
creating.
moderating this discussion because you don't understand basically any of the fundamentals of physics. Why are you moderating this discussion if you don't understand?
Because
physics?
we're trying to come. What I'm trying to do is I'm trying to listen to what people are saying,
You're just confusing
I'm
all
trying.
the issues.
No, we're
I'm
just simply trying to figure out, Harry, why there's more than one pulse in a photon. Why is it just not a single pulse? That the length of that pulse, which is the wavelength,
explained it. Let me do it again. Let me explain it again. You have the pulse has got energy in it, and the photon is really should be called a quanta of energy. So it's all the energy that's in that thing, which physicists call a wave packet. You understand what I'm saying? It's the total energy that's in this whole entire wave packet. Okay. Now, how do you get that energy? The energy is the flow in time. So you've got slices of energy that get emitted at each interval of time. So you have to add up all those time intervals and all the energy that's in the wave packet. That's what Hans is talking about.
What are you using for time?
Huh?
Well, I don't see
Hans
it as
is
being
talking
that
about
complicated.
multiple waves, not a single packet. You know, you can't use a Fourier transform on a wave pulse and say the wave pulse contains all these sub waves. That determines the shape of the wave pulse, not the number of waves within the wave pulse. You're using a Fourier transform type concept.
Yeah, that the problem is that with static waves, that's no problem. But if the wave is moving, and you then take a wave package, then the wave package is dispersing. All these waves run with different, the phases are running away. So you don't keep a pulse. In this photon, in the one-dimensional solution, this shock wave keeps together. That's the property of
But
the
you can keep a pulse.
equation keeps the thing together. It stays a pulse.
But you can keep a pulse. You can keep a pulse in a tensor field.
It does, and as the
it does not. A transverse wave does not disperse in a tensor field.
Well, can I try and answer Corey's question? Can I please, without?
Sorry.
Because I'm just trying to come up with a way to answer his question.
Yeah.
And the way I see it is that these shock fronts are generated randomly. And so what we have is a series of pulses, all with the same length. But when we look at it from far away, it looks like a green frequency because they overlap each other, but they're fundamentally made out of individual little shock front pulses. That's how I would see it. I don't think they chain up.
But you have no mechanism for making multiple pulses. You just said it's made of multiple pulses with no definition as to why it's made of multiple pulses. You haven't answered anything.
No, we've answered that. Can I please answer that question? Can I please answer that question?
Okay.
Okay. Let me answer
Ringing
that
bell.
question.
Ringing bell.
Well, that is part of it. The thing is that in order for an atom to generate light, it must be continuously excited. So it must be continuously like in a spectral
It can
bulb.
send out
When
a
you're,
single.
can I please answer the question?
Yeah.
Can I
If you
please
could,
answer the
yes.
question? At least let me finish my answer, and then you can break in. Okay.
Can we start using flags?
No, but please try not to break in while I'm like halfway through my explanation. The same thing for other people. If they are halfway in their explanation, please wait for them to at least finish their sentence, just as a point of order. So I'm trying to explain how is it we can get these multiple shock fronts. And as I'm trying to say is that in order for an atom to generate, it must be continuously stimulated. Now you have to like fire electrical discharge through a gas, and it is continuously being provided with energy. And so the electrons will be continuously transiting, and so they will continuously create these shock fronts, right? So does that answer it? How that? And as soon as you turn off the energy, no more wave fronts are generated. It has to be supplied with energy.
Yeah.
Does that answer that question?
No, it does not. It just means you just generated multiple photons by energizing.
No.
Exactly. That's what I think it is. It's generating multiple photons.
Franklin phrased it properly, but he has to include that all photons have the same duration. So you, in this duration, in this cycle, you create one or 7 or 20 or 100 different of these pulses. And each time you create a single pulse, you create a bit of energy. So in that way, an atom can send a quantized energy.
So all photons have the same wave.
From one mode to the other, it must spit out a certain amount of energy. So it must spit out a certain amount of these shock fronts.
Okay, so
it does it in one cycle.
Okay, let me just ask Hans. So all photons then have the same length from beginning to end of the photon with with multiple cycles within that length.
Multiple shock fronts within that length.
Multiple shock fronts within that length, and that's the way you envision the photon.
That's how it works.
Okay.
Do you agree with that, Corey?
Well, I'm wondering what that length of that one of a photon is.
I wonder also, because then I can calculate if that was possible to measure this duration or to measure that length, because these two things are related. If you know that, you know the amount of points that together generate an elementary particle.
So we have a photon that has a length, and then we also have a photon that within it has a wavelength, and the wavelength determines how frequently the shock fronts occur, which determines its color. But its overall length from beginning to end is supposed to be the same, but we can never have nobody has ever been able to measure how long that length is, or how long that if I'm seeing a photon pass me, I don't know how long it takes for that photon, the beginning of that photon to the end of that photon to pass me, is what you're saying?
That's exactly what I say. I'm very curious.
So a photon can't be real long, because at the speed of light, a photon comes and goes in an instant, right? So a photon can't be 3,265 miles long, because then it takes a second to pass us. So the beginning of the photon to the end of the photon, we don't know how long it is, but we're certain that there are multiple wavelengths within that photon.
Yeah.
I would disagree. I totally disagree. I mean, the one thing that we,
Franklin, you just said that you agreed that a photon was made up of multiple wavelengths, and you explained how that could even occur. And now you're saying you don't agree that it is made of multiple wavelengths?
No, I'm saying that a photon is, like we're saying, a shock front, a single pulse.
No,
a single
series.
photon is a single pulse.
But you just argued against that. You just explained to me how a photon could be made of multiple wavelengths.
No, I said what we were explaining was that how you can get a number of these shock fronts generated by an atom.
Oh, a number of photons now.
No,
yes,
no,
a number
no, no.
of photons.
No,
I'm just trying to explain what I was saying.
Shock front is a photon. A photon is a series of shock fronts.
Hans, we know what you're saying there. So I'm just providing the alternate solution, which is that the one thing we do know about light waves is that it has a fixed length. We call it the wavelength. That's like 990 nanometers for red light. So, but that we know that as if we think it's a wave, that is its physical length. It's not made out of 23 smaller little waves. It's made out of one wave, which is 990 nanometers in length.
Frankly, you're using a dangerous word. It is not the wavelength, it is the duration of the photon. The time it takes for the photon being emitted, or to the time that it takes for a photon to pass by you. It has a certain duration. It has also a certain spatial length because it has this light speed.
Then what is the length of your fixed light pulse? You should have that on hand. How many nanometers is it?
The light pulse is much shorter.
Well, what is its length? You should be able to tell me in nanometers what it is.
It is very, 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 very short.
So what is it?
It's a pulse. It's a very sharp pulse.
Then what's its length?
A shock front has a very tiny pulse that moves away, and a photon is a string of such pulses. And all photons, not just one photon, all photons have the same duration, independent of the frequency. All photons have the same spatial length, independent of their frequency.
See, now that doesn't make any sense because we know photons, they're different because of their frequency.
Yeah, but they can have different frequency, but they have the same length. They have the same spatial length.
No, by the
same spatial temporal duration.
Well, by the definitions of how frequency works, is that higher frequency means shorter wavelength.
Yeah, but it is not a wave. It is a string of pulses. It is not a wave. It has a frequency. That's all similarity there is with waves.
Let's go back to the overall model that we're trying to build here. So we've got electrons transiting from higher energy to lower energy. Now, Harry mentioned where we get that energy from. Now, that energy just comes from the difference in potential energy from the higher to the lower. If you look at the Rydberg formula, that's exactly what it is. It's just a Coulomb potential difference. That's where the energy comes from. Now, depending on how high the electron falls from, you get greater or lesser amounts of energy. Now, what we're talking about here is when we see the difference between a green light and a red light, what is the difference there? Now, I would say that the red light, please let me finish my explanation, that the red light is simply generating shorter length pulses versus the green light, which is generating longer length pulses. But it's a single pulse. Every single one of these photons that we're talking about is a single pulse, and its frequency is determined by its physical length, traveling at the speed of light. That's how I see it.
The space between the pulses is for red light longer than for blue light. The space between the pulses.
Yeah, that's what I'm directly disagreeing with.
Yeah.
That the spaces between the pulses actually doesn't matter. The only thing that matters is the actual length of the pulse.
The actual, yeah, but the pulse is very tiny. You can't say it's a direct delta.
That is what I'm also directly disagreeing with. That what is different between the blue and the red light is actually its pulse length, which is what we directly measure as the wavelengths.
Franklin, can I cut in and share something here?
Sure.
It sounds like he's saying, take, for example, a ruler 1 foot long. Yes, for conceptual, let's say that that is the length of a photon, for any photon. Now, within that 1 foot, you can draw a sine wave that will go through half a foot mark. Okay, so that's a certain, we'll have one peak up, one peak down. But you could also draw the sine wave going through a quarter. You know, so now there's what? There's 4 peaks. So now he has 4 of these shock fronts within that same foot length. And then you can go and draw the sine wave through the 30-second marks along the foot length. And now he has, and I think that's what he's saying when he says
that's what
you
he's
have
saying.
multiple shock fronts, but the photon's total length is always the same. So there's,
yes, that is what I'm disagreeing with.
You're saying the sine wave goes through the half, but you can draw that sine wave going through the half foot at one full sine wave, or you could draw it with many peaks going through the every 16th of an inch, all through that same foot length. So now that's where the frequency differences are coming from, and that's the frequency you're talking about, and the spacing of these shock fronts that that Hans is talking about.
Yeah, but does that make sense?
I think what the question is, what determines the length of the ruler? Why is that ruler always the same length?
Yeah, it's astonishing for me too.
Here are the opposing views.
That's an unexplained phenomenon in your theory too, is why that ruler is the same length, Hans?
I don't understand it either, but it has to do with the cycle that the atoms are making. The atoms are doing things and continuously in the same cycle, and during that cycle, the photon has to be produced.
Okay, well that kind of, at least that clarifies for me that the reason for the length is undefined and the cause of it's undefined. So that gives some latitude for thought, I guess.
The atom is doing things with in always the same cycle time, and one of these things that it does is producing photons. It produces photons always in the same cycle length.
Okay, so there's some room for discussion there at a later time.
Yeah, well, I mean, this is the major differences here. So Hans is proposing that every single one of the things that come out of the atom has a fixed length. Let's say it's a foot. Okay, but I don't think that makes any sense because we measure light as having a specific wavelength. So I prefer to say that the thing that is coming out of the atom is actually that length. And what I think is actually fixed about what's coming out of the atom is actually the amplitude. We haven't talked about this, but I'm thinking that the actual amplitude of those waves coming out are the same. So whether it's a red light or green light or blue light, the amount of energy that's represented by its peak value is the same. So, I mean, this is trying to explain the photoelectric effect. And if you look at the equation for energy, energy equals HV, which is H Planck's constant times frequency. the only way that can work is if every single frequency has exactly the same amount of energy, so that a red light and a green light for any one pulse actually contains the same quantized energy. The only reason why red has more is because you're getting more of those pulses per second than green, because it has simply a shorter wavelength. So that's how I see it.
Yeah, you're good in that respect with the amount of energy, but the energy is distributed in small pulses and not in waves.
I would agree with that. I'm saying that if you were to look at light individually, you would see it coming in as individual shock fronts, not a continuous wave. So this is different than like radio waves. Radio waves do, in fact, if you looked at a radio wave, put it on an oscilloscope, you see it is a continuous up and down wave.
Yeah.
But I think if you were to put light waves under an oscilloscope, you would see, I mean, you wouldn't be able to see this on an oscilloscope, basically. You would see the individual shock fronts come in at random times.
You will see, no, not at random times. They are equidistant. They come they make really a frequency, because they are equidistant and in time and in space.
That gets back to Corey's questions of how could the atom possibly coordinate that? And I don't think an atom, being a random process, could coordinate the shock fronts into neat, orderly packets like that. I'm thinking that a photon is an individual bump, and that that atom just creates these bumps randomly. We see it, it looks like a continuous wave, but it actually isn't. I mean, it's actually a superposition of these individual bumps, but it's distinct from a continuous wave. So I really don't see the need to put it into a continuous train, because it's just a lot easier to think about it that way, because we're just kind of thinking about this whole thing, and I'm just thinking about how can we make this work in the most intuitive way.
Well, I don't necessarily disagree with Hans's possibility that there are wave packets. I'm looking for the mechanism, trying to understand what within the atom would cause that. I could see a single pulse, but I don't see what within the atom. So I don't, I'm just looking for that answer. And there's room for discussion there to try to figure out why it would do such a thing, as opposed to just generating a single pulse. But it's certainly possible.
Well, isn't the most logical solution is that it can only generate single pulses? That's what I'm suggesting.
I think to really understand that, we need to understand more about the structure of the atom and how it's designed. And there's a lot of differences in how we talk about the atom, obviously. And like I said, my view is strictly waves, and I think Hans's view is pretty much strictly waves that are all initiated by trigger events that are hopping around. But basically, outside the trigger event, I believe everything is shock fronts, I guess, and the shock fronts combine to become waves, if I understand it right. But
well, they produce a frequency,
somehow.
But that's all the similarity with waves that there is.
Right, but it basically is all about there is no distinct discrete component outside of the field. It is basically everything that exists that we observe is a distortion and or dynamic gradient of the field created by the shock fronts.
You must keep in mind that these photons can travel very huge distances, and these shock fronts can do that. Waves cannot do that.
Right. Well, we'll talk about that separately, Hans, if you don't mind.
Yeah.
Maybe I'll get a hold of you and not take too much time here on the site right now, going through those details.
So what do people who don't have a dog in this fight think of the discussion? So we've been trying to, or at least I've been trying to, listen to what people have saying and then try and mold it into kind of a new theory here. So not anybody's particular theory, but
Why do you
and
think
what
it's
we've
so
been trying to do in here.
discussion to create a new theory? You know, I mean, to me, you just bring in a lot of ideas that have nothing to do with physics because you don't know anything about physics. Then we get into a discussion of a particular theory and which is couched in a particular terminology, and then everybody starts arguing over that. As moderator, why don't you create a discussion that can be focused on understanding what people are talking about rather than confusing it all? I mean, I'm sorry, but you know, this whole discussion is completely confused.
Well, the approach that I'm taking is to listen to what people are saying. Now, obviously, people have different ideas. Now, this is like a stew. So you go and you put all the different ingredients in this stew and see whether you can mix it up and come up with something that tastes good.
You're putting your ingredients into the stew too, you know,
Yeah,
which
I
is really
definitely
based
put
on
my
a lot of
own.
the fact that you don't really understand what you're talking about, you know, which is one of my main complaints. You say Hans is wrong because he doesn't
Well,
agree with your pet theory. And then everybody else says, oh,
no,
that guy's wrong
we're
because
trying
he
to mix
doesn't agree
everything
with my
together.
pet theory.
I don't, brother.
Well, that's why I'm asking. That's why I'm asking. What do people think about that? I mean, are we coming up with something that sounds like consensus? I mean, like I said, everybody is putting in their ingredients.
I have no idea what anybody said. I just hear a bunch of, you know, I have no idea what's been said, basically. I'm
all right,
completely
so
confused.
so Harry is completely confused. So how about, let's see, what do we have here? Like, Jim, I know you usually have some opinions. So I'd just be curious as to say what Jim is thinking about the discussion. Just kind of like a fly on the wall.
Well, I agree with some parts with what you're saying, and some parts we really need to understand what a pulse is. That it has an amplitude and a width, and the width defines the fundamental frequency, how many wave transitions there are in that pulse, and as a duration in terms of the length, of how long, how many pulses, how many sine waves of the fundamental frequency are present, start and finish. So that's what you call the length of the pulse, I guess.
Well, do you think we've made any progress on, say, the question about whether light is a particle or a wave?
I think the biggest problem here is everybody seems to dance around the idea of ether without really accepting it. Because as soon as you talk about a wave, you got to talk about ether. You got to bring in ether, and the whole point of photons originally was that there was no ether. That was just some kind of magical.
Well, Jim, this is Harry. You're kind of getting to my point, which is, okay, if you talk about a particle is no ether. If you talk about a wave is an ether. So what you have in quantum mechanics is wave-particle duality. So what you have is you talk about a particle, which is a model, which doesn't have any ether in it. And then you talk about a wave, which is a model which does need an ether in it. So to me, that's really the big conflict there, which is how can you talk about physics being something that has two completely different models in it?
That's why it's so effed up.
Well, I think
and it all goes back to the second postulate of Einstein. That's what screwed everybody up.
I think we got some consensus. That I think that we think that in the case of light, that the photon is as far as the wave particle duality, and I think most of us are looking at the ether or a field which we consider the ether, and the photon being a particle in the sense that if we define a particle as a packet of energy, then we have a particle. But if we don't define a photon as a packet of wave energy, then we don't have a particle. So
But a
it's
packet of
basically,
energy is a nebulous concept. I mean, energy is either kinetic energy, the movement of matter, or potential energy, the potential to move matter, like a spring cocked.
yeah, well,
You can't just say energy without really.
that's pretty much.
Then you're getting into new age, energy and.
You say energy is the movement of matter, but the definition of matter is equivalent to energy. So now you're balling things up even deeper.
Einstein's idea. That doesn't mean it's right.
Well, actually, yeah, it is right, but I mean, not okay. Actually, it agrees with my view. Okay, I'm not going to say it's right.
Believe the second postulate. As soon as you accept the second postulate of special relativity, you're done.
I just agree that energy and matter is basically emergent from energy, shape of the dynamics of energy, and particularly intention energy. So, but that's getting way off subject here.
Well, actually not.
It's more about the definition of a particle. It's still the subject.
Let me just
Because
add right here is that I consider that electromagnetic energy is purely a wave with particle-like properties in some cases, and particles are purely particles like electrons and protons that have wave-like properties.
Okay, but you have wave-like. Then you have to describe the distinction is that the characteristic of the media that's waving.
Actually, it's very simple for particles.
Is it?
The de Broglie wavelength defines an oscillation in the velocity of a moving particle.
But what's a particle?
Well, just think of a billiard ball, okay?
No. That's the thing.
You have to. I mean, with the
a billiard ball is definitely a particle.
But a particle is a packet of energy.
Well,
and that's where we get into the definition of a particle. Because in order to define a particle, you have to define what ether is.
Mass energy has it's a ridiculous idea that I strongly disagree. And I disagree.
Well, we're getting towards the top of the hour. I want to see whether I get one more opinion in here. I know Bill hasn't been saying very much, so I was kind of curious what Bill might, what he's thinking of our little stew that we're trying to make here.
Well, there's a lot of confusion, I guess you would say, in the scientific field. For instance, Maxwell's equations, as currently taught, doesn't include longitudinal fields, just transverse.
Bill, could you stick with what we're trying to say here rather than
I know, but what I'm saying is the equations we've been talking about are not the general equations of electrodynamics. They're very specific, limited equations. And so,
well, actually, we haven't been talking equations. We've been talking
we talked
mostly about about how photons are generated by atomic processes.
Yeah, the wave.
When they come out.
If you don't know what an electron is, how can you even talk about that? And you don't know what an electron is. And so there's, and what we talk about ether. What is the ether? We don't have any agreement on that. And so there's just a lot of things. And the reason why we don't have agreement is we can't agree on the scientific method. We can't agree on how to develop models and theories. We don't agree on the use of logic. All of those things we don't agree on. And so we can't make progress until we find a way to start getting agreements.
Let's see if we can have you define a particle then, because that's what we were just talking about, is what a particle is.
Right. Okay, now I use the oldest known definitions of particles. These are by the natural philosophers, the Greeks, the Indian Jains, the Persians, the Babylonians, the Assyrians, and even Moses. And what do they say? They say that all of the universe is composed of monads. And what are monads? Rings made of the electromagnetic field. And those monads never go away. Once they're formed, they continue. And a particle that has a property of mass, such as an electron, is constructed of multiple monads. And those monads are, when they are in a particular structure, they can have a vibrational energy. That vibrational energy is called mass. And that vibrational energy, you can derive the forces between two electrons, and you can get the force of gravity, the electromagnetic force of inertia. All those forces you can obtain directly from electrodynamics if you use all the empirical equations of electrodynamics to define electrodynamics. But Maxwell didn't do that. He only used 4 of the 6.
Okay, just a minute, Bill. Let's backtrack a bit because you said that monads are in the electromagnetic field. So the field exists outside of monads, or monads are...
The field is the only thing that exists.
No. Okay, and so the monads are basically gradients or gradients or... Okay.
Well, this is an entirely different, because we haven't really discussed this. I was actually hoping to get your opinion on
what I'm saying is
the particles.
We're not even considering what philosophers had to say for thousands of years. We're going on our own.
Right, but you're saying the monads are the particles, and the monads are...
No, monads are not the particles. They're the building blocks of particles.
Okay,
monads don't have these properties that you can measure.
But the monads are basically built from the fields.
Yeah, they're structures in the field. They're standing waves called solid.
So fundamentally, it's the field is fundamental, and from there you build the monads, and the monads build the particles.
Right.
Okay.
And then you get the properties of mass and charge and these other properties that we talk about, but they're not fundamental.
Right, but fundamentally, you're saying that the particles are built from the field. They are the structures of the field.
Right. Everything that we talk about in physics is the structure of the field.
Okay, so that gives definition to what you consider a particle then.
Right. And so, for instance, I have published the structure of all known elementary particles in terms of monads. And I can explain, in terms of that structure, all the decay modes, the reaction modes, the measurable properties of those particles like charge, magnetic moment, those type things. And you can predict the mass. No current with no adjustable parameters. For instance, in the standard model of elementary particles, you use between 19 and 29 adjustable parameters represented unknown physics. But here you don't need it.
Okay.
Don't go too deep there, Bill.
Well, we're getting towards the top of the hour here, and so I'm sure we could go on for forever. But
well, I'm just observing, Franklin, that what Hans is saying and what Bill is saying and what I am saying are very close, but they're quite different aspects of things. But fundamentally, it's all characteristics of the field that define the particles. The distortions or the gradients in the fields that are defining particles. We all look at it slightly differently as to how those fields are initially distorted and what the distortions are, but it is the patterns within the fields that create the matter. Okay.
Yeah.
I'll let you summarize.
Yeah. So I'm going to go ahead and try and summarize. So we were starting out with the topic of what are photons. So I knew this would be a fun topic because everyone would have their own little opinion. So my strategy was to try and elucidate what those opinions are. And we were going to mix that all together into stew. And I was going to try and see whether we could drive together to any commonalities. So, but first we heard from Hans, and he says that a photon is a shock front. And then we were discussing
No, I don't think that's what he said, Franklin. I don't think
well,
that's what he said. That's a problem I have.
well, I'm just trying to summarize here. Then we had this difference of being what is a soliton and what's a shock front. So I think maybe we found some commonalities in there, in that we thought that the photon, I mean, we could almost agree on the shock front kind of terminology as being like a single pulse kind of thing. Then we were talking about that, what is the distinction between photons and, say, regular radio waves? And I think we were thinking that photons, generally speaking, come from these atomic processes from the electron transitions. And that, so it's generally still like a wave-like phenomenon, whether it's a shock front or a soliton. But the characteristics are that it's non-dispersive. So in that way, it's like a particle, and that, a particle is non-dispersive. It goes and you send it off in some direction. It'll keep on going that direction. But this would have to be some kind of thing which would be non-dispersive, and it appears to have some kind of finite length or size. Now, there was some discussion about whether we could then call that a particle. I mean, I suppose, and definitely some people are, that if you have like a wave which is of specific length and travels in a specific direction, it has a lot of particle-like characteristics. So maybe that's where the confusion is, but fundamentally that thing is still a wave. And then there's some discussion about what a particle is, especially because a lot of people consider particles being made out of waves. And there was some discussion about whether that's possible or not. And there was this, and that, of course, gets into this whole particle wave duality thing, which mainstream likes. And then finally, we got through all of this, and Jim mentions that if we're talking anything about waves, then we have to start getting into an ether, which we didn't get into at all. So, like I said, I didn't think we were going to come up with any great amount of commonality, but I think there was some. So perhaps some progress was made, and the purposes of these discussions is to just let people express their ideas, and I think we've probably at least accomplished that. And there are some new things for people to think about. So, so that will do it for this week, for February 28th, 2017, in the Natural Philosophy Society. And I thank everyone for contributing. And once again, if someone would like to have a specific topic in mind, you can bring that up next week. And if you have want to do some discussion on this, you can bring that up in our new forums. So if you didn't like some of the things that were said, or if you like some of the things they said, I encourage you to go ahead and discuss that in the forum. All right, so thanks everyone, and see you next week.